The architecture of the internet is like an hourglass. At the top, apps. At the bottom, all the ways bits are moved around. At the thin waist, the Internet Protocol, IP, the common language for connected devices. All internet traffic moves in this single format, yet it carries a stunning diversity of information, including
cats. In 1998, when about 4% of the world had internet access, GeekoCat was shared on a Japanese bulletin board and it had a message, "Please go away."
Geeko's message, like all internet messages, was split into IP packets and sent from the board's host to hosts of users around the world.
When Roomba Cat was uploaded in 2013, almost 40% of the world, about 3 billion people, had internet access. And IP still defined the net, describing how to transmit data packets from senders to receivers. The simplicity and ubiquity of the hourglass's thin waist enabled amazing growth.
Today, the internet connects over 51,000 so-called autonomous systems. The net carries a massive amount of content, relying on complex machinery above and below IP for its global scale.
To watch a video, you click on a link or paste it into a browser, requesting the video's webpage by its URL. The domain name is translated into one of CatTube's many IP addresses by the Domain Name Service, or DNS.
To create a secure channel to the host, the browser uses the TLS protocol. Through that channel, a request is made for the URL using the HTTP protocol. CatTube generates the page for that URL, containing another link to the video.
Given CatTube's huge audience, the video is hosted on a content distribution network. CDNs hold copies of content on different hosts across the world and deliver the copy most effectively located for each viewer. The larger a site's audience, the more services like CDNs are necessary, or content won't efficiently reach viewers. Based on data from Cisco and Friskies, we estimate that CDNs will carry 8,000 minutes of cat videos every second by 2019.
At that scale, a lot has to happen just to request a web page by URL and have it delivered. There's plenty we're leaving out, like how IP packets are often encapsulated inside other IP packets, or how addresses are translated between private networks, like the one in your home and the public internet at large.
And the details of how security works, as IP itself didn't incorporate security into the original thin waist.
As the net continues to grow, securing it becomes more complex and crucial.
To address these challenges, an idea emerged, a new internet architecture named data networking. Based on what has made IP work so well for connecting the world, but also on how the internet actually came to be used, NDN proposes a new thin waist, a new fundamental protocol.
What NDN is really trying to do is replace the notion of the IP address as the fundamental unit of communication, right? So the internet architecture, much like the telephony network that came before it, is built on the notion of a point-to-point communication channel. And that turns out to be very difficult to secure and very difficult to use to do data distribution over a wide area, which is what most of the internet is being used for today, request and receive data to multiple places. So NDN essentially removes this idea of a channel altogether. Instead, the fundamental unit of communication is a name of a piece of content. It doesn't matter where that name comes from or to. In fact, it can be cached anywhere in the network, and two devices that are passing by each other in a public area could exchange that data if it's the data that one of the requesters wants. The way that you know it's the data that you are requesting is that every piece of data is cryptographically signed, which adds a building block of security in the architecture that does not exist in IP, that was never intended in IP, because the current internet architecture, the IP architecture, wasn't designed to do what it's currently doing. It wasn't designed for security. It wasn't designed for manageability in the context that people are trying to manage IP networks today.
IP sends packets from a source address to a destination address. In NDN, there are two types of packets: interest and data. An interest packet requests data by name. A data packet contains that named content, along with a digital signature, and is sent in response to an interest.
NDN enables an app to ask the network for what it wants, without worrying about where the data is stored. This model is inspired by how many modern apps work already, at upper layers.
NDN specifically has been thought about by one person for at least 10 years, Van Jacobson, as a result of really looking very closely at traffic and topology on the current internet for a long time, and finally stepping back and considering that the architecture is rather inefficient for what it's trying to do today and quite difficult to manage and secure. So NDN is an attempt to take what we know the internet is being used for today and likely to be used for in the future and build a better fit underneath, like build something better under the hood that can support not only the use of the network, but how people write applications for the network.
Like how a web browser works via HTTP, requesting content by its name, the URL clicked or pasted into the browser. And in NDN, you can still watch
Cats. And much of the machinery to do so is at the thin waist. When you paste or click on a link, your browser issues an interest for the first segment of the content you want by its name. When the next node upstream receives that interest, it looks to see if it has the requested data. The node checks its content store, a fast temporary memory or cache. If there's no local copy of the data, it looks up for the longest matching name in its forwarding information base, or FIB, and forwards the interest out of the face, corresponding to the prefix.
A face represents anything with which the node can communicate. A wireless link, a cable connection, storage.
As the unanswered interest is forwarded to the next hop, it leaves a breadcrumb, recording the face from which it came. This information on the state of the request is left in the node's pending interest table, or PIT.
The interest traverses the network node by node. Each node checks its content store and records the interest and the face from which it arrived, until that interest reaches the first node with matching data. Imagine my phone was recording and publishing a live video. Interests find the data by name from any of the phone's faces. Duplicate requests get aggregated. Caches answer common requests. It empowers my phone to become a publisher.
The difference between NBC and YouTube was that NBC was in the business of figuring out how do I architect an audience, and YouTube is in the business of thinking about how do I encourage an audience to start making videos of their cats and sharing them with, a million other people, right? That's a fundamentally different insight about what the business is about.
That opens up a huge set of research challenges, very rich research challenges. First of all, naming itself, because now if everything's about the name, you have to figure out the namespace design turns out to be very important. And the way NDN works is that it's application specific. Every application can have its own namespace design. And then you have to figure out how to do routing on names. So routing is now an open research area.
The Internet of Things, or IoT, a new networking frontier, interconnecting the many devices in our lives.
Connecting devices is one thing, but securing them and making it easy to write apps for them is another. Many propose using IP, making new layers to support IoT apps and their new technologies. Big players can afford this, but what if there was a better way to interconnect the world's devices?
NDN actually opens a new opportunity because I can express semantically what I actually want. The name points to something that I actually want. Like I can have a name that defines an area and an object inside that area. That area may be geographical or like a type of car or a specific parameter. And that can be defined semantically, basically free me from the need of knowing the node.
With NDN, there's no need to acquire an address for each face just to ask the net a question. The car's apps issue interest by name for traffic info, roadway statuses, or manufacturer updates, all using the same thin waist.
Devices use names directly. Data is secured by signatures. Interest data exchange, plus in-network storage, enables disruption tolerance and multipath, multicast, ad hoc communication.
All at the thin waist, enabling upper layers to focus on supporting innovative new applications rather than twisting themselves into pretzels achieving the basics over IP.